Hello all. I think we will start the webinar now. Welcome again to our Rare Earth Roundtable series organized by EIT RawMaterials and the MAGELLAN Project, which is coordinated by Orano. So this time the topic is on technologies and innovation in collection, dismantling, recovery of permanent magnets from end-of-life products. So this roundtable will focus on one of the most critical yet often under-discussed part of the Europe's secondary rare earth permanent magnet value chain. The step between end-of-life products and the recovery of used magnet secondary rare earth element feedstock. In previous case, we have discussed several times on not only in other platforms on recycling of the permanent magnet, but largely that's on the downstream side. After you recover the permanent magnet, either you go for short loop or long loop recovery of the either magnets or the oxide form. So here, as I said, we organized this with MAGELLAN Project, which aims to develop and demonstrate in an operational environment a novel and disruptive, cost-competitive, environment-friendly solution leveraging functional recycling, highly advanced process for manufacturing permanent magnets, and new optimized designs for electric vehicle traction motors. So here today I have 4 speakers representing the rare earth permanent magnet value chain, especially related to collection, dismantling, sorting, and new solutions. And the first speaker, I would like to introduce our first speaker, Laura Melandri. She is a strategic development and innovation specialist at EoL, compliant Italian organization. And she works at the EU project team, focusing on circularity and recycling initiatives. In her role, Laura is involved in several European projects where many of you may have been part of, and especially the projects on recycling aspect is Harmony and Permanect, and also Inspire. So Laura, I welcome you to the webinar and provide your perspective on this topic. And floor is yours. You can share your slides. And to the audience, we welcome your active interaction in the webinar. You can type your questions in the Q&A box, and we will address this. We will have enough time for the discussion after all the presenters, make their presentations towards the end. Thank you again. Laura, floor is yours. Can you share a screen?
Yeah, thank you very much for your introduction. Now I'm sharing my presentation. Okay. Okay, can you see that? Okay. So, good morning, everybody. I'm Laura Melandri, and I work for Iron Compliance Organization that now I'm going to briefly introduce. The Arion system is one of the most important multi-consortium system in Italy for the extended producer responsibility. Our role is the one of managing the end of life of different kind of waste. The whole system is made of 6 different consortia that are related to different waste streams. For example, we have Arion We that deals with the domestic and professional waste from electric and electronic equipment. Arion Professional is for the professional we. Arion Energy manages the battery and accumulator waste. Arion Packaging is for packaging waste, as well as Arion Textile is for the textile waste. And finally, Arion Care takes care of the tobacco products waste. The Arion Consortium is an organization made by and for the producers. And finally, we have the Arion Compliance Organization that is the horizontal non-profit company that provides all the services to the 6 different consortia. But where do we specifically operate? Here we have a simple scheme of the end-of-life value chain of, for example, electric and electronic equipment. As we can see, we have that the producers, since they are responsible for dealing with the end of life of their products, have to pay a fee to a consortium such as Arion to cover the cost of the logistics and transport of their waste and for their first treatment in a treatment plant. So the consumers have to bring their waste to a collection point that is then collected by logistics operators and brought to the sorting and treatment plant. Finally, we have the clearinghouse that regulates the competitivity between the different producers' responsibility organizations, assigning to them the target volumes that they have to collect in dependence on the volumes that the producers associated to that consortium have declared to have put on the market during that year. Specifically, what do we mean with electric and electronic equipment? In Italian, we have 5 different categories for categorizing the waste. The first one is made of temperature exchange equipment with fluid. So we have equipment such as refrigerators or air conditioners. The second category is other large white goods, such as washing machines, dishwashers, or ovens. Then we have TVs and monitors, and also IT and consumer electronics, lighting equipment, pad, and others. And the final categories is lighting sources such as lamps. But why are these electric and electronic equipment waste so important? Because in some of these devices we can find permanent magnets. Specifically, we can find permanent magnets in electric motors in which they are located in the stator or in the rotor. So they are in compressors, motors for motion generation, and also for propulsion. So in practice, we can find this magnet in air conditioning devices, drills, washing machines, motors, wind turbines, but also light electric mobility means of transport, such as scooters and hoverboards, in electric vehicles and in drones. Then we have magnets in signal conversion devices, such as hard disks, loudspeakers, speakers, and headphones. And finally, in products dependent on magnetic fields, such as magnetic resonance imaging, so in medical equipment. Even though permanent magnets are found in many different streams of waste, it is important to assess their quantity to understand which are the most relevant waste streams that are the ones in which permanent magnets are found in the largest quantities and their quality is also high. So, for example, if we investigated the wind turbines, in which the quantity of permanent magnets is very high, since it could go from 80 to 700 kilograms per megawatt installed, but the recovery is a bit difficult because of logistical difficulties. Then we also investigated some home appliances, such as hard disk drives, AC compressors, and washing machine motors, and also MRI, so medical equipment, in which the quantity of magnet is high. Then we also have electric vehicles, in which we did a quantification of volumes with scrapyard and car producers associations, and we found out that the magnet weight is of 1,750 grams. And finally, we identified a very promising flow for long loop recycling, which is the light mobility transport. This is highly relevant because the components in which the permanent magnets are embedded are very recognizable among heterogeneous waste streams, and also the composition is pretty uniform. Their weight goes from 165 to 200 kilograms. Using this data of about the quantities of magnet and the data about the equipment, the waste equipment that are found in Italy and also in Europe, we can do conservative estimations of the quantity of neodymium that is embedded in the magnets that are contained in waste. We can see that these quantities has increased in Italy from 2015, in which it was 9 tons of neodymium, to 2021, in which it was 14 tons of neodymium, while the put on market, so the neodymium contained in the products that are currently on the market, was of 95%, 95 tons of neodymium. And then we can also extend our analysis to Europe, obtaining a quantity in 2021 of 400 tons of neodymium that corresponds to 1.6 kilotons of magnet. These quantities correspond to the collection rates of 2021 that were 17% for Italy and 30% for Europe. So these quantities could be potentially recovered without furtherly increase the collection, but also highest quantities could be recovered if the collection rate would be higher. But recovering these the components that in which there are permanent magnets is not so easy. For example, it is hard to trace this component inside the waste streams. First, because permanent magnets are identified by custom codes when they are standalone goods to be traded. So there are codes that distinguish the permanent magnets in which rare earth elements are contained, such as neodymium, praseodymium, dysprosium, and samarium. There is a specific code also for other magnets and for also ferrite magnets. But once the products in which these magnets are contained becomes waste, there are no such codes that can identify the presence of magnets inside this product. So there is a bit of a traceability issue that should be addressed because in Europe is highly, as we know, is highly dependent from the Far East for the production of magnets. In fact, we can see that the production supply chain of these devices is made of these following phases. At first, the mixed rare earth oxides are extracted, and then they are refined to obtain the magnetic alloy precursors. Then, through alloy synthesis, the magnet alloy powder is obtained, and these powders are used to form sintered magnets and also plastomagnets. Finally, the magnet can be assembled into the product. The issue is that European actors are almost absent for all the upstreams part of the supply chain, and they are present only for the final part of the supply chain in which the final products are embedded. For this reason, to try to make Europe more resilient and independent for the supply of critical raw materials and magnets, since they are important components for the energy and digital transitions and for the space industry and defense industry, the Critical Raw Materials Act established some targets for the extraction, processing, and recycling of critical raw materials. In particular, for 2030, Europe should recycle at least 25% of the annual demand of permanent magnets. And this is a very ambitious target. So we have to understand how to recover these components and the magnets. We have two possible routes that we know. So the first one is the long loop recycling based on hydrometallurgical recovery, that is more versatile in terms of final properties and in which the material are recovered and reintroduced in the supply chain before refining. And then we have the short loop recycling based on hydrogen decrypitation, which has a lower environmental impact and reintroduce materials before magnet forming. Two important players are in Italy are Italium for the electrometallurgical treatment and the startup Rare Earth for hydrogen decrypitation. But before going under one of these recycling processes, it is important to collect the materials that contain permanent magnets. Here, as we were seeing before, the electric and electronic equipment waste from the collection point arrives to the end-of-life treatment plant, in which the components are dismantled and then shredded. Here we have the first critical issues related to the high heterogeneity of the waste streams that are found in the treatment plant, and we have also the lack of dedicated separation stations for magnet-containing waste. So often the magnetic material is dispersed during the shredded phase, and is no longer recoverable after that. But if we are able to collect a product that contains permanent magnets, the first thing that we have to do is a pre-treatment that is done first extracting the component through manual or semi-automated dismantling. Then the component has to be demagnetized through heating in a oven up to 400 degrees, and finally the magnet can be extracted. Also here we have some issues regarding the very high cost of manual disassembly, both in terms of time and economic aspect. And at the same time, it is difficult to implement an automated disassembly line because the variety of products is very high. And finally, we don't have specific and specialized players for the pretreatment. The first option for recycling is, as we know, the long loop recycling, but also here we have some issues other than the ones that I have already mentioned for the identification of the components containing the magnet, because the long loop recycling based on hydrometallurgical recovery is very complex. It required several chemical processes with a high consumption of chemical reagents, so it is difficult to make it economically sustainable. And at the same time, in Europe, we lack of actors that can do such a process. The other option is the short loop recycling based on hydrogen decrypitation. This process is more simple than the previous one, but at the same time it has more constraints on the feedstock in input because the feedstock has to be homogeneous. And the magnets cannot be oxidized or have coatings because otherwise the hydrogen decrypitation would not be effective. At the same time, also virgin material is required to make new magnets. Since there are many challenges regarding the end-of-life value chain of permanent magnets, there are many European projects in which we have been involved or are involved to address these issues. The first one I want to mention is NURE, that has been completed and has done a pilot plant for the automated HDDs disassembly and their hydrometallurgical process. This pilot plant has in input 20 tons per year of magnets, but its industrial scale-up is already in progress because from the progress achieved by Nuri, the INSPIRE project has started. The objective of INSPIRE is to establish the first industrial plant in Europe for the recycling of rare earth elements from spent neodymium iron boron magnets. The plant will be located in Ceccano in central Italy, and it will process permanent magnets from electric vehicles motors. The expected outcomes of this project are for the first level of the plant, the permanent magnets disassembly line that will have an input 1,000 tons per year of rotors to be disassembled. And then the second level plant is the hydrometallurgical recycling route that will have an input in 2026 500 tons per year of magnets, and this input will increase to 2,000 tons per year of capacity in 2030. Then another important project in which innovation in the end-of-life value chain of magnets are developed is permanent. In permanent, I want to focus on the mechanical pretreatment and disassembly line developed by Politecnico di Milano, in which rotors from electric vehicles motors are disassembled through these phases. The first one is the magnetic field inspection, in which the quality of the magnets is assessed. Then we have the thermal pretreatment through induction heating to demagnetize the magnets, and then the rotors can be disassembled through semi-automated and automated operations to finally extract the magnets mechanically. Finally, other than all the important technological innovation, I want to stress also the importance of the collaboration between the different actors of the value chain and their connections with each other. For this reason, in Permanent, a digital marketplace named Critics has been developed to connect the upstream and downstream actors of the value chain, and to connect also all the actors that want to buy volumes of spent permanent magnets to be recycled and to find viable volumes that otherwise would be fragmented. In this way, also visibility, traceability, and access to market data are improved. So, what can we say in conclusion? We have seen that the permanent magnets are a strategic source of critical raw materials in end-of-life components. The recovery potential is very high, but now is still limited because of poor traceability and separation challenges. The main technical and economic barriers remain the pretreatment, dismantling, and also the feedstock quality. But the magnet recycling can support Europe's goal for autonomy, circularity, and also industrial resistance. Finally, we can say that all the pilot projects, dedicated infrastructures, and digital platforms are important to build a sustainable European value chain for permanent magnets supply. Thank you very much all for your attention, and I think I can stop my sharing. Okay.
Yeah, thanks, Laura. Very excellent presentation. Looking most of the aspects in the recycling of the permanent magnet value chain. We have a couple of questions, but I will raise this towards the end of the webinar. And I remind the audience to put their questions in the question answer box. The next one in our presentation is Simon Kuhn. He's from Group Comet, a company headquartered in Belgium, but also operation in France and Germany. And Comet and Simon is part of the MAGELLAN Project. The company's main business is, of course, in the collection and dismantling of the end-of-life products. And he's the lead researcher there. Simon, the floor is yours. And yeah, please share your presentation.
All right. So thank you, Nabil. So today we're gonna present a bit what Comet has been doing, what we've been developing in the Magellan project, and what are our activities linked to magnets at the moment. So the part of the value chain we cover is really from devices to magnets. So I think Laura was mentioning the need for a specialist player in pre-treatment. This is what we try to do. So quickly about the group, to correct Nabil just here, we are mainly in Belgium, a little bit in France. Our major sites are around Mons and Charleroi. So we have a bit more than 400 colleagues. We handle 1.2 million tons of metallic waste. So the core business really is shredding and post-shredder treatment for all the base metals. But we also evolve into becoming the leader in Belgium for the recycling. And as such, we have been developing recently some more specific value chains, and rare earth magnet is one. I think Laura had a very good presentation about the importance of and magnets. So to discuss a bit more in details that aspect of our work, I wanted to present what we've done in the Magellan project so far. The first step for us, and it was crucial, was to map the urban mine and understand really what was the potential of different devices in our collection schemes. So first of all, we observed the rare earth contents among several different devices. We've mentioned small electronics. We've mentioned mobility vehicles, but can be also large white goods, can be other type of devices. And here, I don't want to repeat too much what has been said already. I agree with most of it. A crucial point was really to understand the penetration of the rare earth magnets among different devices. For example, you might find a very interesting source of magnets. We've mentioned headsets, we've mentioned, I don't know, here the example is washing machines. They can contain a few hundred grams of magnets, but you need to make sure, if you want to start a recycling process, you need to make sure most of them are rare earth magnets and not ferrite or other type of magnets that we do not really consider here in this work. And I think that was one of the major bottlenecks at first for the mapping activity. And then finally, among the devices we had selected, we had to assess the recoverability. And I will move on with that. The three main streams we selected were the electric vehicle traction motors, very classic e-bikes and e-scooters. Once again, like Laura mentioned, were the use cases that were quite interesting for us. So we sourced them and we provided those magnets to the Magellan Consortium. And then finally, what we took from that is we developed some dismantling protocols. We understood what were the right tools to process and extract those magnets. How can we optimize the logistic? I think it's one also of the great bottleneck. You have very small volumes of magnets, yet you need to ship large volume of waste. So understanding how that works. And finally, trying to solve this extraction process and finding the best way economically to extract the magnets. So this is what we've done in the MAGELLAN project. And now I'm going to tell a bit more about what is the current situation of our activities. So concerning first the EV stream, what we started doing now and what we do on a regular basis is manual dismantling to extract the rotors, and then we use a thermal process to demagnetize the magnet and to allow the extraction. So at the moment, in the past year, only a few kilos were extracted. And the reason is simple. It's because simply we don't see the volumes of electric vehicles reaching end of life yet. And I think the market is much more on production scrap at the moment. And what something very critical, and I think I will be able to comment on that in the following slides, is that you can see on the picture here, the rotor of the car finally is very small compared to the amount of material you receive. So the business case really relies on the valorization of the base metal as well, copper, aluminum, steel, and magnets is just an add-on to what's being done already. We couldn't only recycle the magnets and throw the rest. Obviously, that's not the goal here. But to have something that works out economically, you really need to take into account the other metals as well. So what are the barriers at the moment and the risks? It's clear that manual dismantling still is a very high cost. Like I said, very few vehicles reach end of life. And why manual dismantling is the option we opted for. First, because we had the capacity and it was very fast and very flexible to start the activities. And it's clear that the designs we see are constantly evolving. And so at the moment, we would like and we would try to have some more optimized or automated process. But it's true that the variety of designs we see is such that manual dismantling still allows us to be flexible at this point in time. So this is quite a large risk for more, let's say, dedicated processes. And finally, the price dependence. I will show that visually to you in a few slides. But it's clear that we do all of that expecting the price of magnets to be attractive. And yet the price of magnets, it's very much governed by the price of virgin material from China and by the demand of the different constructors. So there is a high risk also for this whole value chain trying to set up here. And so, like I said, the perspective, we still try to improve the extraction process, and we expect in the coming years to have much higher scrap volumes, which will help us scale up a bit this part of our activity. And the second aspect of our activity was the light mobility stream. So this is a bit, this was a bit easier for us to start because simply there are larger volumes already available. The lifetime of e-scooters and e-bikes is much shorter. And there the approach was the same: manual dismantling, thermal process, extraction of the magnets. Last year, we've been able to extract 5 tons of magnets from those streams. So I think it's quite promising to show that we can do it at a, let's say, large scale. And here the barriers are quite similar, but there is an emphasis on the collection. For cars, obviously, you have big volumes quickly. Here, when you have only a few hundred pieces, a few hundred vehicles at somewhere, the collection becomes quite tricky to be able to have a profitable collection and recycling. So there is also a lot of agility to find there. The variability is a bit lower than what we see in cars, so it helps us also adapt and have a very a streamlined process to do that. And the price of rare earth is just as dependent in this case. So we talked about automatization. We've seen a few examples already. It's clear that this is one of the use cases where we could think about implementing some type of automatization, but all the time it's going to be assisted by humans. It's not going to be just like I load the scooters, I load the wheels, and the magnets are going to come out. The solution is going to be hybrid. You still need some flexibility, but here it's a bit more homogeneous, and we could expect having some type of technological response for these processes. And then now moving on to what it means to the business model, and I think this is where most conclusions will be drawn, is that, of course, you need to valorize all the material. You can see here on the left that a scooter wheel is a lot of copper, a lot of aluminum, and then finally a small amount of magnet. And it's even more the case for EV rotors. And so the two point we can drive, and then I can comment a little bit the figure I present here. The two very important points that come out of our experience so far is that the margins in this process at the moment are very low. So for us, it's more a matter of strategic positioning and being there to support and to close this new value chain for Europe, rather than being excessively profitable at the moment. Because we're directly competing with the Chinese raw materials. And so the question I will ask, and this is a rhetorical question, is shouldn't we think about having a European price for those magnets and pay the price of sovereignty? I close there the debate, and maybe we can touch on that at the end of the webinar. And then finally, valorizing all the base metals. And this is what I wanted to show on the graph here below. You see that actually the magnets, it's the third material that brings value behind copper and behind aluminium. So you cannot just think I have an e-scooter, all the value is going to come from the magnets. No, you really need to valorize all of the materials. And the final comment I will make is that we can see also, so on the right, you see all the expenses to do the operations and to buy the material. And on the left, you see the revenue streams. And you can see that actually the expenses overcome the price of the base metals. So if it wasn't for rare earth magnets, we wouldn't open the wheels, we wouldn't do all of that. They would be shredded like usual. So the price of the magnet will really be the driver, and will ensure we recover them or not if the prices are too low in the future compared to the operating prices. So this is a bit our experience. So don't hesitate to get in touch with me if you have any question or would like to go deeper. And I will give back the speech to Nabil. Thank you.
Yeah. Thanks, Simon. Yeah, again, very, very interesting observations, especially from MAGELLAN and what Comet is doing. Yeah, again, the challenges, pre-treatment, dismantling, cost, price, and competition from the Chinese side. And we'll have some discussions later of the webinar. So the next one, part of the MAGELLAN project, they do the work together is with University of Liège. Here I have the speaker, David Bastin. He's taking lead on the a little bit more in between in the recycling business on sorting. Maybe they have some new scope for that and how to manage this for a competitive permanent magnet value chain. Bastin, David, the floor is yours.
Yes, thank you, Nabil. I'm sharing. Is it in the presentation mode for now? Not yet?
Not yet. Yeah.
Okay, so I'm from the University of Liège in Belgium, and in Magellan with Comet and another recyclers, BLC. We were mainly involved in the upstream part of the recycling chain, from dismantling down to the extraction of the magnet. And at the university, we were particularly focusing on the extraction of the magnet from the component. So, well, as Simon mentioned, we were mainly focusing within Magellan on the e-mobility, looking at the cars value chain, and also the light mobility value chain. So Comet and BLC started from the equipment, from the device itself, extracting the motor block and then extracting the rotor from the component. And we were looking at the thermal demagnetization and setting of the magnets that were further treated by CEA or Technalia. So our main contribution was on this first part of the value chain, and as it was already mentioned, well, the urban mine, it's a large array of design and composition. So what we learned during Magellan is that we have even within a category like cars or scooters, the design can vary greatly in terms of geometry, in terms of the way the magnets are set in the rotor from surface mounted to inserted, glued or not glued with polymer glue or with ceramic glue, or even mechanically tied in the rotor. So you have to be flexible and to adapt your treatment to be able to extract those magnets. And this is why, and Simon mentioned it, that full automation is not really possible for now with what is on the market, and you have to adapt and collaborate also with manual dismantling. So this is what we learned. The large array of design, but also the large array of composition, even within a category. When OEM purchase magnet, they purchase the magnet according to the application and according to the performances of those magnets, the remanence, the coercivity, the Curie temperature, the corrosion resistance. And when those magnets reach the end of life of a product, and for the recyclers, the composition, the real composition of the magnet is unknown. And for the recycler, the value is in the composition and mainly in the rare earth basket that you have in your magnet, and particularly the content of heavy rare earths. As you can see here, the price of heavies, this is a Shanghai market price, internal market in China, but I have also here mentioned the CIF price for Europe. You can see that for heavy rare earths like dysprosium or terbium, the price can be very high, terbium at $1,000 US dollar per kilogram. And you can see that it's decreasing towards the light rare earths. So the content of heavy rare earths is really driving the basket value that you have in your permanent magnet for the recycling loop. I have done some calculation during Magellan. So we had several models from e-cars, from light mobility, from wind turbine or hard disk drive. And I calculated the basket value of the rare earths contained in 1 kilogram of those permanent magnet. And you can see that depending on the composition, the value can vary from 40 US dollar per kilogram for a low quality magnet used in an hoverboard, up to 120 US dollar per kilo for a sports car. So it's really depending on the heavy rare earth content and the heavy rare earth value that you have in your magnet. It's not only a question of value, but it's also a question of environmental impact. As these heavy rare earths are very low grade in the ore and are recovered at the end of the process, the environmental impact of extracting the heavies can be much higher than extracting the light. So I also put here an estimation of the CO2 equivalent that was emitted for the production of this rare earth basket for each category. And you can see that it can vary a lot. For low quality with only light rare earth, you have 20 kilogram of CO2 equivalent per kilo of magnet. I'm coming back to the hoverboard, or for high-end magnet, high application, you have spent much more, more than the triple in terms of CO2 equivalent. So it's not only important to know the composition of the magnet in terms of economics, of business, but also to what you will do with this magnet in order to lower the footprint of your recycling loop. And this is why we think that we have to develop, or there is a need to develop sorting tools for sorting the magnet according to their composition and mainly according to the content of their heavy rare earths. And to direct the different magnet quality to the right recycling loop. As was mentioned in the first presentation by Laura, you can have the direct route with a reuse, a reshaping of the magnet, or the hydrogen decryptation. You can have the pyrometallurgical route, where you will have vacuum induction remelting and then use of the ingots, and you go to powder metallurgy. And you have the hydrometallurgical route, where you do the leaching, the rare earth separation, and the metal production. So I think it's important to direct the right chemistry or the right magnet quality to the right recycling loop. And if you want to refunctionalize, for example, the heavies that are in magnets like cars, if you want to remobilize the dysprosium of the terbium, maybe you will have to direct it to the hydrometallurgical route, where you will be able to separate the heavies and to reuse it in a efficient manner, like a grain boundary diffusion method. So it is very important, we think, and this is why we are developing sensor-based sorting technologies. In the lab, the team have mainly worked on developing these sensor-based automated robotic sorting for scraps, metallic scraps, aluminum, but we are now moving to try to diversify this application to the sorting of the magnet. As you have to sort them according to their chemistry, you have to have sensor giving you an idea of the chemical elemental composition. So this is why we are mainly working on the development of dynamic LIPS, laser-induced breakdown spectroscopy. You can see it on the images, where we are shooting with a high-frequency, high-intensity laser on the metallic piece and recording the spectrum to have the composition of the pieces. So this is what we are developing. This is on the right, one of the prototypes that we have at the university, and I think that we try to move also to the sorting of the different magnets. As was mentioned earlier, when you look at the different application of those neodymium iron-boron magnets, there is a lot of dispersive application. A lot of application where you have very small magnet dispersed in a component with very low value. The main promising streams for the recycling being, as Simon mentioned, the electric vehicles and also the wind turbines. This cover only by 2030 nearly 40 or 50% of the application. So it means that a lot of applications are quite dispersive, and I doubt that for more than 40% of the magnet use, we one day will recover them. So we have to take it into account when preparing a business for Europe. And it's just an illustration here. If we collect 50% of the items containing the magnets, which is very high and very optimistic, and at the dismantling phase, we have 95% recovery, at the refining 90%, and with the remanufacturing 95%. If you multiply all these recoveries into different steps, you will have 40% recovery. And this is only in one loop. So in the second loop, you will have even more, less than 40%. So it's very important to understand that. Yes, recycling can contribute to the optimization of the use of the resources, and it can really contribute to lower the environmental footprint of the value chain. But the contribution of the recycling for securing raw material supply and towards sovereignty will be limited. And the primary mining remain the key for the security of the raw material supply chain. So it has to go hands in hand. Europe won't survive only with recycling, so we have to focus on primary mining. And this is really a message I would like to share with you. And some other lesson learned and a summary here, lesson learned during the Magellan Project. So as mentioned, a large variety of component designs and permanent magnet composition, so challenge for extraction and dismantling and extraction. Important dispersive use of the magnet, preventing their economic recycling. The cost of dismantling versus the magnet value. So when reaching the recycling phase, the chemical composition is unknown by the recycler. And we think really that the sorting of magnet according to their composition, mainly the type of coating, the chemistry of coating, and the presence or not of heavy rare earth content would improve the economics and the environmental footprint of the value chain. So recycling contribute, as I just said, to the optimization of the resource use and lowering the footprint of this value chain, but primary mining remains the key for the security of raw material supply chain within Europe. And yes, we have to develop our mine in Europe, but we also have, if we want to move fast, to establish international strategic mining partnership to really secure our raw material supply. Thank you.
Thanks, David. Very interesting presentation, especially the work you're doing in the Magellan project, and also good to see the different composition of magnet, even the same application. That's really a challenge, and especially you mentioned in the classification, especially for the HDD, you said lot 1 and lot 2. What exactly is this? Is it different HDD you mean?
Yes, different lot that we received, different brand that we received.
Okay.
Well, it was many. One was from one manufacturer, and the other one was a mix of different HDD. So it can vary also within the HDD categories.
And is composition is different?
Yes, I think if we go back to the result, the composition is a bit different. Yeah.
Okay.
But on a HDD, maybe Jakub has more insight about the variability of the composition. Yeah.
So thank you for again your presentation. So now I will move to the next presentation. Our next speaker is Jakub Salkiewicz, and he is a scientist, technologist, businessman, and founder of the Phoenix Source SPU company based in close to Warsaw. He did his PhD in metallurgy. For last 4 years, he is developing an advanced technologies for recovery of CRM from e-waste and other EoL equipment and materials. This includes robust HDD recycling technology developed with EIT raw material support. We did fund a couple of his initiatives, and as well as robotized AI vision sorting of hard metal scraps developed under the EU Horizon project rescue tool. So, Jakub, the floor is yours. Please start your presentation.
Thank you very much, Edward. Yeah, pretty difficult to spell the surname, Jakub Szałatkiewicz.
Yeah, sorry for that.
No, it's fine.
Yeah.
It's always difficult. Yeah, I'm representing Phoenix Surowce, which is a Polish private company. As Nabil mentioned, we are doing a project with EIT raw material support regarding recovery of critical raw materials as well as other base metals. Because as it was mentioned before, only focusing on one type of metal for recycling is never beneficial unless it's gold. Yeah. So the rest has to be approached like in a holistic, let's say, way to address every bit you can find. Yeah, we are a private company from Poland. We are involved in some of the R&D projects with universities and other and other companies, and we are mostly focusing on automation, robotization of difficult processes for disassembly of computer hard disk drives and for segregation of various and difficult to segregate materials such as hard metal scraps with the robotized sorters.
Jakob, can you make it the presentation mode? This, yeah.
Is it visible? I thought it's
visible, but with your side slides.
Okay. I have it in the presentation mode, but it's showing not in the presentation mode. Maybe I'll. How is it now?
No, it's coming. Yeah.
Okay.
Yeah. Good.
Maybe I'll use this one. Yeah. We are focusing on processing waste of electronic equipment and other waste for recovery of critical raw materials and the base metals. So I won't be talking a lot about the magnets, as the whole thing is Roundtable and MAGELLAN Project is about the magnets. Just a brief summary. We're not recovering, recycling almost any of the rare earth elements in terms of Europe. So this is very very at the beginning really of the whole recycling, as we recycle like a 90% of the copper and aluminum, a little less some steel, but with the terms of rare earths it's almost nothing. This is below 1%, and we are mostly reliable on the external sources. As David mentioned, it won't be possible to supply EU economy and at all the production of new magnets equipment without the primary sources from mines, from mining. However, I think, and I'm very enthusiastic about that, I think we can go forward with recycling and supplying a lot of the share of EU economy and EU production from secondary sources, which are the waste of electronic equipment as well as other types of wastes. But in terms of rare earths, it's mostly this source. Let's go to the next slide. Okay. So the upstream and let's say the value chain, well, I have to repeat that it's already been said that the main things are the collection and then a proper treatment. So what we have to focus on is on one hand to recover the rare earths because they are valuable. Well, in terms of economical, that's the interesting thing. In terms of economics of the recycling of rare earths, they don't really play a major role. Just like Simon mentioned, and I think David also showed that. If you, I had a funny situation talking with one of the magnets recyclers in Europe. They wanted to buy the magnets from us. I took them to the let's say local Polish, the biggest wheel recycler in Poland, and we were discussing the e-scooters recycling. They were showing, oh, we want these magnets from this equipment, and they said it was like 2 years ago. And they said, yeah, what will be the price? How much you gonna pay for the magnets? Yeah, and the guys asked, and the recycler said, okay, €1. Yeah, we said like, okay, it ain't gonna even pay us the bills. Yeah, I'm not mentioning to make any margin. So it was completely abandoned. But the thing is, what I want to say that if the prices of the recovered magnets will go up, the whole value chain will restructure itself by itself. Just the new methods will be developed. The new, let's say, sources will be found. It will be just like on itself, because the recycling sector is very interesting. If the recyclers will found some, let's say, this gold in some sort of equipment, they will go after it. Yeah, they will buy the stock of the market. They will organize themselves. They will develop new applications, new for first manual disassembly, and then picking up of the cherries, and then they will provide the materials. It's possible. It will happen by itself. Then there is a next step, the automation and the reduction of the costs and so on, so on. But it has to be like a margin or value driven. So nobody will be disassembling the equipment if there is no value for the operation. Comet Simon had a very good slide that he showed that it's like a 5% or whatever, and then there is 85% for the dismantling and the whole operation of the cost. Yeah, but this is how it is. In case of our hard disk drive disassembly, we're applying the robots and AI vision and machine learning and this and that tools to do that. It's like if we would only focus on the magnets, it's not feasible. It's not worth doing. Yeah, you can just close the company and that's it. So you have to sell the aluminum, with the high quality aluminum, sell the steel, sell the printed circuit boards, or process them further, and then just sell the magnets just as a byproduct. Yeah? And the price matters because if it's 10 euros or if you see the prices of the virgin materials like a 60 euro per kilogram of magnets, this matters, yeah, but it cannot go higher than, let's say, 30%, 30 euros, because if the virgin is 60, then nobody will pay this amount of money. So this is very important, and we're going to the let's say main thing that okay, the collection is pretty good at Europe. However, it's about 50% of the equipment officially collected. Then, when you have them collected, then you can find the equipment which contains the rare earth elements, and then you focus on them. And then you find out that in the headphones, the magnet is so small that it's not worth shredding or doing something with that. Maybe there are some ways to do it, but then you have to incorporate what are the contaminants with that. Some materials you can shred, but then if you're shredding everything, you lose them. But if you shred the headphones, maybe there is a way to segregate them, but then you have to have the separate flows for them. So for each rare earth, you have to develop separate flow, separate material collection, and separate processes, and then separate operations to get them. So this is very, very demanding for today, and that's why most of the waste are shred. And when they are shred, because of the volume and the mass you have to process, you lose the things that you find valuable. Yeah? And it's not only about the rare earths, it's about gold, tantalum, and other metals, which are palladium, also inside those material end-of-life equipment. Yeah, so I spoke a lot about this slide, but the next one will be, let's say, faster. Yeah, so as we know that there are some waste or end-of-life equipment containing the magnets, we can go after them. And for now, we know that the magnets are in the hard disk drives, electrical vehicle, motors, wind turbine generators, e-scooters, e-bikes. There are some also in the compressors, heat pumps, and some other in speakers, tools like power tools, hand power tools, and others. And probably that's the most of there was also those MRIs and other things, but there are very, very little on the market. And we have the situation that currently in Europe, we have pretty well funded and beginning of the development of the magnets recycling industry, but without the feedstock they can process, everyone is going after those categories we have here, right? Hard disk drives, electric traction motors, and wind turbines. Yeah, everyone is bidding for one wind turbine, which is being disassembled, for instance, in Europe per month. Yeah, so everyone is trying to get those 200 or 500 kilos of rare earths. Well, on the other hand, it's better to reuse it than recycle the whole thing, but that's another question. So we have those materials we can go after, and then there is next step. Yeah, if you have the compressors or for instance heat pumps or other things, you develop specific processes. However, today, as for instance in electro recycling company, this is one of the biggest companies in Poland for recycling in Europe anyway. They have like a line for the fridges processing. Yeah, so they take off the compressor, they take off the fluids, and they apply the foams and this and that. And then they have the compressors. And this is something that the compressors are already on the market available. So there can be another step for post-processing of those materials which are already disassembled from the fridges, unless they are shred completely. And then in some of them, this is the case. In some of them, there might be rare earth elements, yeah, because most of them are ferrite. So it's again, you have to check which ones they have, the rare earths, and which are not, and then you find that it's only like a 5% of them, or maybe more, maybe less. And then you said, okay, it's not reasonable to just go after some 1 or 2% and just sell it or shred it or do something else. And that's why they are lost. Yeah, so the main thing is that we don't have really proper technologies, and we have to shred most of the materials to recover the base metals mostly. There are some operations about the printed circuit boards that we are pulling aside, even with manual dismantling, and the rest is going into shredding, and then we lose the rare earths, and that's why the rare earths recycling is below 1% because of this thing. Yeah. So to change this perspective, we have to look on the other side. So if we identify where the rare earths are or other valuable things, then we develop the process to separate those things, and then take care of them. So and then the rest of the whatever equipment can be processed in the currently done way, but it's very demanding to do something like that, as you have to handle every one bit of equipment based on itself and then pull out the materials. So it's very demanding. And then, as I mentioned, it's like a mixed or ferrites or rare earths or other materials. The one of the things that we have to look when we are developing such a systems is that we have enough feedstock. And if we're looking on those ways, the e-scooters are being currently growing on the market, so we can go that. After that, we can go also after the electric motors, but they are still not enough volumes. Then we have the hard disk drives, which we are approaching, and this was the selection, yeah, that we have them on the market, we have them segregated, and we can develop the technology to disassemble them and recover the magnets and other metals. To be honest, when I started with the hard disk drives, it was years ago, I've calculated the magnets as a steels, yeah, as a ferrites, just together with iron and other materials. And then just by the way, we became developing the ways to demagnetize them, segregate and concentrate them. So this is something that has to be looked at. And every operation with robotics and selective disassembly, dismantling is very demanding. Even with the hard disk drives, it's very demanding to develop the system which will be allowing to process, for instance, for 3.5-inch drives, about 250 types of drives. Yeah, they are different. Yeah, forget about the design for manufacturing, for recycling. Yeah, this is just a fairy tale and storytelling. Yeah, even the big companies doesn't care about that. They just care about selling, not recycling. Recycling, then the recycler has to think about it. So this is very strange. And even in terms of hard disk drives, I have the same type of hard disk drives, and on one from 1 year I have the screws like a T8 and Torx 8, and on the next one I have T6. Yeah, it's the same construction, the same drive. It's just that platters or the electronics is different. So or the idea that you have 6 screws T8 and there is T6 or T7 even in the middle. Why this one couldn't be the same? Yeah, like just unbelievable how complicated this can be. So yeah. What we are doing is really focusing in Phoenix on disassembly of hard disk drives. We developed the system. We are now developing the second one for the small ones. for the 2.5-inch drives to process the hard disk drives. And you can see one of our systems, we call it DiskBot, under the now RoboCycler project with RawMaterials, which is disassembling the hard disk drives in an automated way, like the manufacturing line where the drives are going one by one. We have such a system. We're now doing the pilot, and the idea is to have like a few plants of HDD disassembly across Europe. Each plant as a base will be like a 40 tons per month of hard disk drives on the input, and this will generate the amounts, for instance, like a 4 tons per month of the magnets assembly. However, this is magnets assembly, and the magnets inside the magnets assembly is about 20-25%. So it's like a ton per month. Yeah? Not a lot, but on the other hand, we're processing 40 tons per month of hard disk drives. You can always upcycle that to bigger volumes. But then you have to take into account the collection, the transportation, and the handling of everything. So, but the most important thing is that for this technology, we are having like a 99% of the recovery of all the metals. Yeah? It's not possible in any other technology. And next to that we are recovering 99%, we don't have to post-process or segregate the materials because it's not shred. We are recovering like a full materials like aluminum chassis, magnets, printed circuit boards. They are high quality, so this is also a different value, different approach. And so the next step with the magnets, as we are focusing on the magnets, is the segregation of the magnets from the steel brackets. And we have developed the way to, well, it's a simple thing, just thermally demagnetize the magnets, the steel brackets from the steel brackets. On the magnets assembly, and then it occurs that it's very hard to segregate them because they are in pretty similar shape. The magnets are bent and the steel plates are also bent. So we thought, okay, we have some experience from our one of the Horizon projects rescue tool, where we developed the sorter, an AI vision sorter for sorting of the hard metal scraps. So we applied the same, let's say, technique to segregate the magnets, and it went very well. So we have like a now possibility to segregate on the same machine, just reprogramming it to different types of materials to segregate the magnets from the steel brackets after demagnetizing of the ones from the hard disk drives. This can also be applied to other materials. When we are with the sorting, we have also worked on the increasing of the value of the materials we are recovering from the hard disk drives. So we are also looking into printed circuit boards to segregate them, to identify the types and the types of components on them. So this is also something that we are doing with the AI and automation robotization. And I wanted to say also a few words about the project, which is the source of our experience in sorting and AI vision robotic segregation sorting. This is the rescue tool, where we developed the tool for segregation of various very mixed scraps. And there are hard metal scraps. For now, we are also addressing that the mixed materials, they are end-of-life tools, so they don't really have any change in their maybe they're a bit dirtier than they were during the purchase. So the thing is that we shouldn't be, well, maybe I'll talk about it on the last slide, but this is the example where you can have the machine which is able to sort various and mixed materials which are not similar in any case. Maybe they are long, but they can be broken and so on. So that's why it's very, very flexible. Yeah. But the important thing is that when we are approaching the end-of-life equipment, they are very mixed, they are very heterogeneous streams, and it's very difficult to apply any tailored solutions for that. And that's why shredding is currently used worldwide. But we in Phoenix and other companies also are trying to get some specific tailored solutions to allow segregation and other increase of the sorting and develop new ways to treat end of life equipment. Yeah. So there is no one uniform and universal technology to recover magnets or just treat in automated way, robotized way, the end of life equipment, because it can be dirty, it can be fatigued, and can be in various versions, but it has to be the technology has to be very tailored and very directed onto this one, which makes it very difficult and then increases the capex and the cost. One thing I wanted also to add that is under the rescue tool, we are also developing codes for the end-of-life equipment or end-of-life tools. It is dedicated for the hard metal tools. We are avoiding now to say that they are hard metal scraps, because when you say scrap, this is a category that it's a waste. Yeah. And then if it's categorized under the waste, then it generates a lot of problems in recycling and handling and transportation. I wanted to say that as an example, yeah, you have your laptop or mobile phone at home, you're using that, you're, let's say, sleeping with it in your bed. And the moment when you're deciding to get rid of it, it becomes a hazardous waste. Yeah. So this is like a very strict thing. I'm not against the waste categorization and waste directives and law, but it shouldn't be so, let's say, strict, so very hard to handle the materials, because this affects our chains of supply, the recycling property abilities and volumes. This is important in terms of hard metal scraps, which are very the same as they were produced. There is nothing changing. We just machined a half a millimeter of it, and that's it. It's exactly the same. And in terms of electronic waste, maybe it's dirty, it's used or something, but it's also not like a hazardous waste, and there's not chemicals that's gonna poison anyone because it's lying somewhere, yeah, or you're transporting it from one place to another. So this is something to be considered under some new revisions under the Critical Raw Materials Act or other legislation, which could boost, let's say, or ease in the EU, let's say, recycling sector. And also one thing is what is relating to what Simon said from Comet, that and what we are also affected, that there is an export of end-of-life equipment outside Europe. Yeah. And on one hand, we are saying, okay, we don't have enough feedstock. On the other hand, we are selling it outside to whatever China and other Asian countries, Turkey, where instead of being processed here, as it already is in Europe, we could recycle it and develop new technologies to recycle it. But now they are saying, oh, we won't have the enough amount of hard disk drives to recycle it. And then they are shipped away. And this is exactly the same case with the electric motors and other equipment, which is shipped away instead of being the source of our economy for the materials. Yeah. So these are like two things I would like to have a small input: the coding and the waste directives. Let's say a bit problematic for day-to-day life. Yeah, in Europe. Yes.
Okay.
Thank you very much.
I was requesting you to wind up. We maybe can have a few minutes for question answers. There are many questions.
Yes, let's go to questions.
Yeah, we have 10 minutes or almost 9 minutes for question answers. Thanks again, Jakub, for joining, and very nice presentation, challenges, market, technology, sorting, a lot of information for our stakeholders. So I'll go to a few questions. If time permits, we'll look at all of them. First one is largely on the feedstock. We have, especially for the VE, we probably have a lot of feedstock. especially for Laura, you mentioned, your capacity and also categorization of, especially in Italy, the feedstock, and you say maybe 1,000 ton of capacity by 2030. So where exactly what feedstock that, especially for Italium and Inspire, uh, project. So what are these feedstock you see? This is quite common or a uniform feedstock that can easily be dismantled, then feed into the downstream process of the recycling business.
For
And
the
yeah.
regarding the Inspire project and the treatment plant there, yeah, the feedstock would be especially rotors from the electric vehicles, and these kind of streams is chosen because it is quite homogeneous and also specific, let's say, collection routes can be implemented because electric motors does not fall under the electric and electronic equipment, but they finish to the, for example, car dealerships and other specific actors. So it is already, let's say, separated from other waste streams, and so being that pretty uniforms, it should be easier to recover them because the electric motors are not like mixed with all the others electric and electronic equipment waste.
Yeah, and yeah. So on that, Simon, you said that the company developed certain protocol for identifying the end of life, magnet. Can you explain this, and can this be shared with public or similar stakeholder group? So we have a common understanding of this, if there is certain set of standards we can develop. Yeah.
Yeah, not revealing too much details here. I think the focus was really to try to understand, okay, what were the few key steps of dismantling the different devices, so either electric motors or e-scooter wheels, and understanding also what was the right tooling, what was the right extraction process. So really making sure we do not leave time on the table at any stage, either dismantling, logistic, or heat treatment, to remain very general here. Yes, see if that answers more or less your question.
Yeah. Yeah. Okay. So can this be shared with other groups, or is it just for Magellan or your own purpose?
What I just talked about, I think there's no secret here, but it's clear that we developed specific protocols that we use ourselves.
Okay.
Yeah.
Yeah. And also, maybe it's not right question to you, David and Simon from the Magellan. Have you observed a change in the RE content in the magnet from different time period? Not exactly different feedstock, but same product, different time period. Can you answer? Maybe
Yes, I think David will answer you on that one, but it's clear that the heavy rare earth content, especially in low grade application, has been decreasing strongly. I think David can confirm that.
Yes, I confirm that. And also there is a shift depending on what is available on the market. You can have a shift from dysprosium to terbium, and recently we saw the holmium popping up. So it depends of what is available. What the magnet manufacturer are looking at, it's at performance of the magnet, and then they do the recipe, and it can change. And for the same application, the composition can change from years to years. Even with the same brand, we have several models from Toyota, and from years to years, it's changing, even if it is the same model. So you can reach the same performances of a magnet by mixing different ratio of rare earths. But what you need for high-end magnet is heavy rare earths like dysprosium, terbium, and holmium. So you cannot cut this, or you can lower this by, for example, grain boundary diffusion, and we can see that now it's dropping. The content of heavies in different application is dropping. Yeah, from 6% in the beginning, and now we can have like 2, 3, even 1%. Yeah.
Yeah, and another question, maybe it's related to one of the slides, David. On oxide vs metal feedstock price, but not low prices. Is the
Yeah,
electricity?
what you have to look at is the price on the internal Chinese market and the price that the European producer will pay to have the raw material. So there is an internal Chinese market price, but a European producer that would like to buy this raw material, they will pay twice or 2.5 times the price because China is applying taxes, strategic taxes on this material. So yeah.
And also another question, maybe quite tricky. Do you have any data about how much Europe is treating NdFeB magnets with short loop method, and what is the feedstock? Do we have any idea on that?
No, I don't know. I don't have the numbers in mind, but there are capacities building up. There are big investment in Europe. There are capacities building up. But in 2030, Europe will need 40,000 tons of neodymium iron boron magnets. So recycling, even if the capacity is building, if you reach 10,000 tons, it will be a success. But you still need the 30,000 tons behind. So yes, it's important. Capacity is building, and it industrial process. It takes time. So yeah. And there was a question also about samarium, why samarium is so low. Because in the nature you have much more samarium, so it's more abundant, and the cost to extract it is lower. So this is why the content, the price of the light rare earth is much lower than the one for the heavies.
Yeah, good. Yeah, good answer. And for Simon, one mini process you said is manual dismantling. If the availability and feedstock keep increasing, do you see prospects for other technologies, or is it a technological barrier that you have to do it by manually?
Yeah, I think an important point here to explain is that we started with manual dismantling because we really have the capacity in-house at Comet. And instead of trying to find the right technology and wait for it to be deployed, we said, okay, let's do dismantling, let's do it, and let's gather the knowledge on the different streams. And then we work our way backwards, let's say, to profitability and to try to find proper processes. And so, like I said, for EV rotors, I think it's still quite challenging because the designs are very different. For light mobility, I do think there is a potential for some type of automated dismantling, maybe automated unscrewing, things like that. That could be flexible enough to adapt to the different type of designs. Yes.
Yeah, and there is a question on the development of labeling. Yeah, of course, there is development, and it's also under the CRMA articles developed or proposed by JRC and DG Grow team that we going to have a labeling of the of permanent magnet. Yes, that process is ongoing. Yeah, and yeah, dismantling compressors in which you have permanent magnet. Any best practice to dismantle, either to Simon or maybe to Jakub?
Yeah, every appliance has to be approached separately. You have to cut them open, and then you have to look inside, pull out the motor, punch the rotor, and then look on the magnets. Yeah, so there is a multi-step approach. Yeah, so you can use a lot of things, a lot of tools. Yeah, it's it's too long to discuss, really.
Yeah, I think there's also, when you sort magnets, what would be the criteria to consider to reuse magnets or rather than recycling them? Should be a
Yeah.
question for recycling company, but yeah, Jakub, maybe.
Yeah, honestly, I don't believe, and I will be quite clear here. I don't believe once we extract magnets, we can reuse them as they are. The design evolved much too fast. The size is too design specific, and then you will damage them no matter how you try to extract them. So either, to me, the only reuse possibility is at a component level. If you want to reuse the motor, if you want to reuse the wheel, then yes, we could think about something. But as soon as you extract the magnet, I mean, there's no way you can think about reusing them. Like the component, the design will evolve, and then nobody will certify a magnet that will be extracted and recycled. So then we can start talking about short loop or long loop recycling, obviously, but reuse, I don't really believe in it.
Yeah, maybe for the wind turbines where the magnet are big pieces, you can reshape them, some of them. But you're right, Simon, for many application, it won't be impossible to reuse them.
Yeah, I think we are 2 minutes late, and I think we should wind up here. So it's also largely, I think concluded it rightly. It's also a market problem, and also where in the Europe we stand in competition with China. It's not only about exporting the end of life product or product that containing rare earth permanent magnet, and also after dismantling you have magnet. We have realized you get, if somebody offer better price for that magnet, that's also that can go, even Jakub can get better price in US, for example, not €2 in Europe somebody offered, but even 24 euro per kilogram of dismantled magnet in US or even China. So we have to be also careful about that usage. So with this, but step by step, we are developing in the industry. There are many initiatives and projects, European projects, plus startups and companies building this value chain. So hope this kind of discussion contribute to develop a recycled permanent magnet value chain or hybrid permanent magnet value chain like Magellan is developing. So thank you all, mainly our speakers joining and also participants for joining. So we'll have our next webinar after our summer break. So hope to see you next time. Thank you all for joining. Thank you.